So just to let you know, there's been a slight change of plan because one of the speakers had to reschedule from this week to next. We've moved the poster session where you're going to present your posters to Thursday in the evening. So just let you know that you should have your posters ready, but we'll probably try to get the place ready for you to put up your posters a little bit earlier.
So you mean, is that today?
No, Thursday.
Like this week? Sorry.
Thursday in a week.
Oh, in a week. Oh, all right.
The
Fine.
14th.
Okay.
Will it be only one?
Yeah, that's okay. I'm just a little sorry.
I mean, you can get it out, maybe.
So we'll have to see how much space there is, but ideally we'd like to have all the posters up so that people can have a chance to clean them.
Okay, so hello again, everyone. So in my first lecture, one of the things that I set out to convince you of is that in models of classical frustrated magnets, you can have macroscopic ground state degeneracy, and so long as order by disorder doesn't select a subset of those states, then you have a low temperature disordered system, which we can call an example of a classical spin liquid. And one of the things I said right at the beginning is that this terminology of classical spin liquids, bringing to mind an analogy with ordinary liquids, is maybe a bit misleading, because in ordinary liquids the correlation length is generally rather short, whereas, as I'm going to explain to you, in classical spin liquids you can have interesting correlations and correlation length that diverges as you go to zero temperature. So what I want to do in this lecture is start talking about how you generate a reasonable description of these low temperature correlated states. And what I say in this lecture will be purely at the theoretical level, and actually I'm going to focus after the first section on two-dimensional models, but it'll introduce ideas which will also be useful in 3 dimensions. And in the third lecture, I'll talk about how the ideas that I'm introducing today and extending in that third lecture help us to understand a class of materials known as spin ices, which have some very interesting phenomena. Okay, so the question is how we understand these highly correlated but still disordered states. And there are a series of approaches that you can take. And what I'm going to begin with are the most simple-minded ones. And in fact, I want to start off by talking about mean field theory. So you may feel that you didn't travel all the way to this summer school to hear about something as mundane as mean field theory, but all the same I think it's worth just a few minutes to understand actually why it doesn't work, what it is that goes wrong. And it's also a good lead-in for something that's a little bit more sophisticated, which does work, which is self-consistent Gaussian approximation or a large N treatment. So if we start thinking about mean field theory, of course you're perfectly familiar with it in one form or another, but sometimes it's set up in a rather phenomenological way. So let's just remember how you can set it up systematically. So what you want to do in general is work out averages by taking a trace of whatever the observable is that you're averaging and normalizing, and I'll denote this just by an average like that, and then the mean field approximation is to say that you work out the averages with some simpler Hamiltonian. So this is the full Hamiltonian. And this is something that you can treat, so generally it will be a single particle. And then the important thing is that the free energy that you're interested in is bounded by the expectation of the Hamiltonian taken in this simpler ensemble minus temperature times the entropy in that simpler ensemble. And then because this is a variational bound, we can adjust the parameters in our single particle Hamiltonian so as to minimize the right-hand side and get our best estimate. So if we think about applying this kind of approach to any magnet, including a frustrated one, then we have, from the expectation of this Hamiltonian, the exchange times the expectations of spins at different sites. And then, if we're interested in studying the transition, we'll expect these local magnetizations to be small, so we can expand the entropy in a power series in the magnetization. And this is something that we know from being able to solve the single particle approximation that we're taking, which will have some local fields in it to generate these magnetizations. So when we do a Taylor series expansion of this, we get a constant and then a term linear in temperature with some constant, and because we're doing a Taylor series expansion and the odd powers vanish, the first non-trivial contribution is this sum of magnetization squared, and then there's higher order terms like that. So then, of course, the idea is to pick these m's to minimize the right-hand side. And so it's obvious that at lowest order we've got a quadratic form here involving the exchange matrix. And so that means that the ordering temperature and also the ordering pattern are identified by the eigenvalues and eigenvectors. In fact, the minimum eigenvalue of the exchange matrix J and the corresponding eigenvector. So, in fact, if I call this minimum eigenvalue epsilon min, then the minimization of the right-hand side has these magnetizations 0 if temperature is large, because this forces them to be 0, but as temperature decreases, we come to a point where the smallest eigenvalue of that quadratic form goes through 0, and the condition is that epsilon min plus this constant here times kBTC is equal to 0, and epsilon min is negative, so this gives an estimate for the critical temperature. And then the ordering pattern simply involves the magnetizations being proportional to the amplitudes of the corresponding eigenvector. So, of course, if you do that for an unfrustrated lattice, then what you find is that there's some discrete set of minima in the diagonalized exchange, and you have an ordering pattern which is unique up to some global symmetries. And things are rather straightforward. So what is it that goes wrong if we try to apply this approach to a highly frustrated system? What goes wrong is that the minima of the exchange, instead of being at isolated points in reciprocal space, in fact turn out to form flat bands. And that means that you don't know which eigenvector the system should order into, and the whole treatment breaks down. So let's look at that in a little bit of detail, which will in fact tie up with things that I was saying in the previous lecture about the origin of degeneracy. Okay. Any questions on anything up to that point? Yes.
Are you considering the thermodynamic limit here?
Yeah, in principle. I mean, for the usual reasons in order to have a phase transition, but I don't see anything particularly delicate about that. Is there a particular point that...
Not sure what you mean by flat bands.
Yeah, okay, that I'm about to explain.
What happens because you may imagine that flat bands are separated from other bands by some finite gap.
Mm-hmm.
In this case, one might think that it's still useful because you could construct a reduced model incorporating only the degenerate bands. A little bit in the spirit of because of treatment of the vortex lattice, you end up with Landau levels which are highly degenerate, but you keep only the lowest Landau level, and you can make a very effective theory within this flat band. Can't we make use of those?
Yeah, it depends what the ultimate physics is, and that depends partly on whether or not there is, in fact, order by disorder, fluctuation-driven order. So if there were, then within the mean field approach that I was talking about, I said that there were, beyond the quadratic terms which I wrote explicitly, then these quartic and higher order terms, and it could be that once you included those, then you'd get some reason to select a particular state from this degenerate band, and in that case this whole approach would be a natural one to take. But there are other situations where we know that a system doesn't order, that there isn't this order by disorder phenomenon, and in that case you'd be led in the wrong direction.
Just when you say a discrete set of epsilon mean, you mean a discrete set of eigenvalues for J?
Yes.
You can pick the minimum value easily.
Yeah, sorry. So I had a simple example, but then I was worried that I was insulting too many people. But if we take a square lattice with nearest neighbor exchange, then you can diagonalize Jij by taking a Fourier transform, so you get a J of Q, and then, as I'm sure you recognize, you get a J of Q, which will just be cos Qx plus cos Qy. So then the epsilon min would be at Q is pi pi. That's the kind of thing I had in mind. Okay, so by flat bands I mean, bands, I suppose. I'm using the terminology because it's always natural to at least block diagonalize the exchange matrix by Fourier transform. Of course, in the kinds of lattices that I'm talking about, where you have, for instance, in the Kagame corner-sharing triangles or in the Pyrochlore corner-sharing tetrahedra, we have several sites per unit cell. So we block diagonalize the exchange by Fourier transform, and that gives us some finite-sized matrix, which we then diagonalize to get a number of bands. So what I'm saying is that the minimum of J forms a flat band.
Is it the same case on the triangular lattice, where I don't have a unit cell, but I still have frustration? Do I get one single flat band?
No, so there you get discrete minima, in fact, at the corners of the Briand zone.
Okay, so there I have some sort of order.
Well, I'll talk about that later on in the lecture, and whether you do or not depends on the type of model. So, for instance, with Heisenberg or XY spins, you have an ordered ground state, although disordered at finite temperature because we're in 2 dimensions. But with Ising spins, as I'll explain in detail, it turns out that you have a disordered ground state. So if we think again about corner sharing clusters, in the way I was talking about in the previous lecture, if we want to think about the eigenvalues of this exchange matrix, then we can think in a variational sense about taking the expectation of the matrix in a particular vector with constraint that the length of the vector is 1. And if this is the exchange matrix for nearest neighbor interactions on a lattice of corner sharing clusters, then you can rewrite this as, for the same reasons that I talked about in the previous lecture, square of a sum over clusters of the sum within each cluster of the amplitude plus a constant. And the point again is that if I expand this square, then I get cross terms involving coupling of all the different phi's within a cluster plus a diagonal term which is just the sum of the squares of the individual components, which is fixed to be a constant if we fix the length of the vector. So we minimize this expectation if we minimize this term. So this is this sum over phi should be 0 for a minimum eigenvalue. And then we can do the same kind of Maxwell counting that I talked about. So if we think about phi, then it has some number of degrees of freedom, which is simply the number of sites, the number of spins in the system, and then in principle -1 from this normalization condition, but I'm only going to keep the counting up to, I'll keep the extensive terms and drop the ones that are of order 1. And then this constraint to get the minimum eigenvalue is that the sum of the components for each of the clusters in the system should be 0. So these constraints simply in number the number of clusters, and if I express everything in terms of the number of clusters, then the number of spins. If I have q spins in a cluster, each shared between 2 clusters, the number of spins is q over 2 times the number of clusters. And so the number of states with this minimum eigenvalue is f minus k, so that's q over 2 minus 1 times the number of clusters. So, in other words, it's extensive for any of these frustrated lattices, because the smallest value of q that I would take would be q equals 3 if I'm thinking about corner-sharing triangles, and so I have some positive coefficient times the size of the system. So, if you look at things for the Kagame lattice, so we have 3 sites in the unit cell. So that tells us that we have 3 bands. And this tells us, if we express it in terms of this tells us that 1 out of the 3 bands is degenerate with this minimum eigenvalue, and the remaining 2 will be dispersive. And if you look at the eigenvalues for the different bands as a function of wave vector, then what you find is that there's some minimum band like this and a couple of dispersive bands if you take the wave vector in a particular direction, and this dispersive band touches the minimum band at a particular point. And for the pyroclaw, we turn out to get 2 dispersive and 2 flat bands, and a similar sort of picture. Okay, so the message there is that because of this macroscopic number of states that the system apparently could order into, when temperature drops below this mean field ordering temperature, then the theory breaks down. And so we can say that mean field theory fails below, and then the temperature which comes out of this calculation is basically the magnitude of the Curie-Weiss constant, which you remember was the parameter that we could extract from high temperature measurements on the susceptibility. Okay, so how can we do better than mean field theory? Well, there's one approach which I think it's worth talking about, which works rather well, although in the end it doesn't bring out the generalities of the long-distance physics, so we'll move on to other things after that. And this approach goes under a lot of different names. I think the most reasonable name for it is cell-consistent Gaussian approximation, but it's also something that becomes exact when the number of components of the spin becomes large, so you can reasonably say it's a treatment of the large n limit, and then back in the early history of statistical mechanics it's equivalent to something that was called the spherical model. So, to explain what it is, in the statistical mechanics, obviously we're taking a kind of trace, and for these spin systems, what that means explicitly is that for every site in the system, we're integrating over the orientation of the spin, but then in these classical models, we have a constraint that the spin length is kept fixed, and it's that constraint that makes these problems non-trivial. So the idea is to relax that constraint and instead to make the trace by taking an integral with no hard constraint on the spin length, but instead Gaussian to stop the fluctuations getting too large. And there's lambda, which is a bit like a Lagrange multiplier. You choose so that you come as close as possible to respecting this constraint, which means that we'll fix this to be 1 on average. And as you can see, the different components of spin decouple here. So in what I write from now on, I'll forget about S as a vector. So let's take this exchange interaction to be J over 2 times an adjacency matrix where this is 1 if I and J are nearest neighbour and 0 otherwise. So then if we think about the problem of calculating some kind of thermal average within this approximation, what we should do is integrals over all the spin orientations, and now the point is that we can form the spins at the different sites into a vector, and we just have a quadratic form in the exponential with beta j times the adjacency matrix plus lambda times the unit matrix. So, for instance, if we calculate a spin correlator, then it's a standard result from Gaussian integrals that we can write that just as the inverse of the matrix that appears in the exponent. And we still have to remember this equation to fix the Lagrange multiplier. So we need to fix that using a diagonal element of this correlator, and so long as all the sites in the system are equivalent by symmetry, then we can just average over all of them by taking a trace. So what we have is that 1 is the trace of beta j a plus lambda times the identity inverse with 1 over n for the averaging. Okay, so to see what this means, it's useful to do a spectral decomposition. So if we say that the eigenvectors of the identity of the adjacency matrix, say alpha with eigenvalues E alpha, maybe I should put a J in there for consistency with what I had before, then this is and this becomes okay, so now if you think about the low temperature limit, when beta j is very large, sorry, I've got an inconsistency here. I think well, all right, I'll leave the j in there and take it out. So when beta is very large, then most of the denominators here are very large and make only a small contribution to this sum, which is just dominated by the terms that involve the flat band. So when temperature goes to 0, beta times epsilon min plus lambda must go to a constant. And this correlator, well, the only terms that survive in this sum over eigenvectors are the ones from the flat band, so that Si Sj goes over to something proportional to Ij, and then a sum over alpha from the flat band of. So in other words, it's proportional to the projector onto the flat band. So within this approach, if we want to study the low temperature correlations in one of these frustrated systems, what we should do is study the interaction matrix, and we'll find that it has a flat band, and we should look at the long distance properties of the projector onto the flat band. And there's one basic point about that projector which it's worth making, although I don't want to follow it too far, and it's to do with that picture that I had of the eigenvalues with a flat band and some dispersive bands. So the projector at a given wave vector is acting in this, in the example from the Kagame 3x3 space, corresponding to the 3 different sites in a unit cell. And it turns out that because 2 bands touch at one point, the projector in K-space has a singularity at this point, and that singularity in K-space, when you transform to look at correlations in real space, turns out to give you power law correlations. And that connects, at least to some extent, with topological things that other people are saying. But the reason I don't want to follow it further is that if we keep looking at things in this language, then we have the impression that it's all terribly specific to the details of particular lattices, whereas if we look at things from other points of view, it turns out that we can see how to coarse grain and get the long wavelength physics out in a way that makes it much clearer where the details of the lattice come in. So at this point I want to move to a different way of discussing things. Yeah.
So these states alpha and I and j are single particle states of this H0, the effective Hamiltonian.
Yeah, well, I'm not sure I'd even want to call them single particle states. I mean, they're just from doing the linear algebra of this interaction matrix. But yes, I mean, if you had fermions hopping on this lattice, then or non-interacting particles hopping on the lattice, then they'd be the single particle states for those.
So shouldn't they be all orthogonal to each other?
Yes.
So then wouldn't that final result there would be just delta ij?
No, because I'm not summing over all states. Because of this weighting factor, if I go to the low temperature limit, the only states that survive in this sum are the ones from the lowest band, which is this flat band. And so this is a crucial point, that it's projecting onto some subset of the states. Thanks. Yeah.
When you make this approximation replacing height constraint by Gaussian, the topology of the state changes. Does it matter at all?
Sorry, the topology of the...
Before it was punctured and there was some non-trivial homotopes, and now they're gone. Are we missing anything crucial?
Yeah, so the answer is yes, clearly we're leaving some things out, and there are situations where that can be important.
Perhaps the ground state is the case. Are there any excitations that we...
Yeah, okay. So that's a good way of focusing in on whether it matters. So if you go into the details of this, then you can calculate a correlation length and ask how it behaves as a function of temperature, and it diverges as you go to the zero temperature limit, and in fact it diverges like 1 over the square root of temperature. And for vector spins, that in fact is the correct result, but if we considering Ising spins, then the correlation length diverges much faster. It diverges exponentially in 1 over t. So certainly there are some things that it doesn't capture. But I mean, I think really the more general point is that this is nice as a quick way, which incidentally gets the short distance physics in at some level as well, because you're starting from the lattice. But what it doesn't give you is a systematic approach to discussing whether the things that you've left out are relevant or not. And that's the reason why you'd like another approach. Mm-hmm.
Yeah, so what is n? You said this large.
Oh, okay. So, I mean, in these models, you can think about n-component spins. So, obviously, the conventional Heisenberg model would be 3-component spins, but we can consider n-component spins. And so the fact is that in the limit, when the number of components is large, this becomes exact. And the reason is basically a central limit theorem. If you have many contributions to the square of the spin length from the different components, then it doesn't fluctuate much.
It's something maybe irrelevant, but still, this picture's on what makes me think. Are there examples when adjacency matrix has non-trivial topological bands?
Yeah, I'm not sure. Maybe.
For that one would need to have a complex J, right?
Yeah.
So it should be in a broken symmetry state. But
Yeah.
still.
Yeah. So if you start with a spin model with antiferromagnetic and possibly some ferromagnetic bonds, then obviously you just have phases of 0 or pi, and then it may be hard to arrange. Okay, so the basic point is that it's no good sticking with the original spin variables in the model, because the statement that we're, for instance, in a ground state or in a low temperature configuration is complicated in that language. So what we want is a description that can encapsulate in some simple way the idea that the system is in a ground state. And then once we've got that description, if we're trying to get some long-distance universal physics, we hope that we can coarse grain it. So what I want to start with, and I'll talk about it in quite a lot of detail, is the triangular lattice Ising antiferromagnet, which is a terribly old problem, of course. It was discussed by Vanier and several other people in 1950, possibly the first example of a frustrated magnet that was really examined in a lot of detail. It doesn't actually fit neatly in with the things I was saying about flat bands, because if we look at the spectrum of the adjacency matrix, as I mentioned in answer to a question just now, it has discrete minima, and that means that with vector spins you have a ground state with 3 sublattice order. But here we're talking about the Ising model, and studying this problem will introduce some ideas which are useful in a much more general way. And the Ising model has macroscopic ground state degeneracy. And I've been saying that the term spin liquid is rather misleading because there are interesting long distance correlations, and in the case of the triangular lattice Ising antiparamagnet, where of course we have an exact solution, we know that the correlator between a pair of spins decays in magnitude. There are some oscillating signs like distance to the minus a half. So clearly that's an interesting kind of behavior which we'd like to understand. So there is an exact solution, but it's reasonably involved, and in any case we'd like to use this to learn about more general approaches for problems that will work when we don't have the exact solution. So if we think about the ground states, then in each triangle we have to minimize the total spin, so either we have 2 spins up and 1 down, or 2 down and 1 up. So we just start for orientation thinking about the origin of the degeneracy by considering some example spin configurations. Then if we take a piece out of the triangular lattice and just think about possible spin configurations, then one possibility has spins alternating up and down around a hexagon. And if we do that, we can see that the exchange field at the site at the center is 0 because we have cancelling contributions from the boundary. And so here we have a spin which can be flipped at no cost in energy. And of course, if we set up a state with local regions like that all through the lattice, then this will give us an extensive entropy. So to have the kind of nice description that I said we'd like over here, it turns out that we can introduce something known as a height model, where the idea is to map from a spin configuration to a configuration of heights on the lattice, and with some conventions it becomes 1-to-1. And to do this, we need, first of all, to introduce a convention for directions on these bonds. So we can say that we'll go counterclockwise around the triangles which are pointing up on the lattice. And then when we go from one site to a neighbour along a bond in the direction of orientation that we've chosen, we can say that the height difference between those neighbouring sites depends on the spin configuration, and we either go up by 1 unit if the bond is unfrustrated, so that means that the spins are oppositely aligned, and we go down by 2 units if the spins are parallel, so that the bond is frustrated. So if I take this site to be at height h, then I'll go up 1 step, going around like that, and another step going around to the 3rd site, and then I go down 2 steps when I cross this frustrated bond. And obviously the point is that this gives us a consistent set of rules for any ground state, in the sense that the height is single valued, because there are 2 upspins and two parallel spins and 1 anti-parallel spin in each triangle. And if we flip this spin, then the heights would be h plus 1 and h minus 1 there. There's one slightly awkward thing about this definition as it stands, and that is that clearly we have jumps in height between every site, and to smooth those out, we can think of the heights as being located not at the corners of triangles, but at the center of triangles, and we just put a value at the center of triangle, which is the average of the 3 corners, which will be an integer if the individual heights are integers. Okay, and then if I apply that mapping to a configuration like this, then I end up with heights at the corners which just alternate between 2 values as I go around the hexagon.
And the middle spin, is it 0?
And then the middle spin, well, it depends on the orientation of the middle spin. If the middle spin is up, then I can copy things from here and I'll get h plus 2, and if the middle spin is down, then I copy things from the other triangle and I get h minus 1. And in either case, I find that the heights of all these triangles are flat, are the same. So this turns out to be a flat configuration. And just to get some intuition, it's worth thinking about what the heights look like for some other possible arrangement of spins. So here I had spins alternating up and down as I went around the hexagon, but another possibility is to have rows of parallel spins with their direction alternating from one row to the next. And if you work out heights in this case, then it turns out that you have a surface in height space which is tilted. So this is a tilted configuration. And in this case, you can see that there's no possibility to flip a spin because that would generate triangles with 3 spins up or 3 spins back down. So it's tilted and it's got no entropy. Whereas this flat configuration has entropy. Sorry, could you say again?
Is it simple to see that if you arrive at the same vortex, if you start from one point, go through 2 different paths and arrive at the same node, it will be consistent?
Yeah, no, that's a crucial thing. Can we see that this height labeling rule is consistent? And the answer is yes, and the point is that since it's consistent around an elementary triangle, it must be consistent around some bigger area because we can make it by putting together triangles and everything will cancel in the interior and you'll just get a contribution from the boundary. So, yes, it would fall apart if that weren't the case. So any other questions at that point?
How do we deal realize this? Problem.
There's one that's studied a lot, but it's it has ferromagnetically coupled chains which are arranged on a triangular lattice with antiferromagnetic coupling between the chains. So you have a complication of a long correlation length in the third direction.
What's the system?
Yeah, I can't remember right off. I can probably find it. Okay, so now we come to the important point. The idea is that we can cause grain and treat H of R as a continuum. And continuum, that comes in 2 senses. I'm thinking of this coordinate now as living in the continuum, although with some short distance cutoff, and I'm thinking of H as taking continuous values. And then we'd like to know what the probability distribution is for H, so we can think of this as Boltzmann weight with some effective Hamiltonian. And then the idea is that the effective Hamiltonian, well, it should capture the entropy of these different configurations, and a flat configuration has entropy, but a tilted one doesn't, so it had better penalize tilt, and we should write down terms which respect translation invariance and inversion symmetry and so on. So the simplest thing that we can write down is something like that. And this is obviously invariant under uniform translations of H, which reflects the fact that our rules for associating heights didn't care about what the origin was. And then if you look in more detail, it turns out that out of these flat states, there are in fact 6, and that's reasonably easy to imagine. There are 3 sublattices on the triangular lattice, and these flat states you generate by putting a minority spin on one of the 3 sites of the on one of the 3 sublattices. So you get 3 states where the minority spin is up and 3 where it's down. So you have 6 flat states, and that means that H plus 6 turns out to be equivalent to H. The other thing that you need to be able to do is to go back to spins. Yes?
Could you just explain again why it's just the H plus 6 equal H?
Yes, I mean it's partly a question of how much detail you'd like. So the short version goes like this. You can separate the triangular lattice into 3 sublattices in such a way that the neighbours of sites on one sublattice belong to the other 2 sublattices. Then these flat states, it turns out you generate them by putting a minority spin on one of the sublattices and majority spins on the other 2 sublattices. And then because there are 3 sublattices, that gives you 3 states for each choice of the minority spin, and those choices are either up or down.
But here we were working on each triangle independently, but for example, if I take, if I continue counting, I start from H there, and I go back all around, I go back H is equal H plus 6 just by not taking each triangle independently. Like the first one is H plus 1, H plus 2, 3, 4, 5, then H is H plus 6.
No, if we attach height labels for a spin configuration that's a ground state, it's crucial that the labeling is unique apart from adding a constant, the same constant to all of the heights. So you shouldn't have an increase in heights by 6. So I mean, my convention was to go counterclockwise around the up triangles, which means that the direction on this bond is like that, so I have to go clockwise around the down triangles. So if I go along a bond in the direction from this orientation, then I go up 1 because these spins are anti-parallel, but on this bond although the spins are anti-parallel, I'm going in the opposite sense to the orientation, and so I go down one, so this is H, and so on. Yeah.
If I want to compute the partition function for this, so the integral over H now goes from, how do I invoke this condition?
Right, so this turns out to be a good way of calculating correlation functions, and in particular long-distance parts of correlation functions, but I guess it's not a good way to calculate the partition function for the original Ising model. I mean, you'd need to regulate it, because if you did an integral over all configurations of H, there's a zero mode, and you'd need to remove that.
In these Gaussian problems, they can be quite sensitive to the presence of some heading.
Yeah, sure. It's something that I'm going to come to in a moment. Yeah. Okay, so the basic point is that we have a mapping between spin configurations and heights, but we need to invert that if we're going to calculate spin correlations using this mapping. If you work out the details, then it turns out that the spin at a particular point is related to the height field by a cosine, and so it's basically cos of H with this factor of pi over 3 appearing because the physical values of H are periodic with period 6. So if I increase H by 6, I just increment the argument of the cos by 2 pi. And this phi is something that takes 3 different values on the 3 sublattices. So it's 0 or plus or minus 2 pi over 3 according to the So that means that if we want to calculate a correlator like that, and for simplicity I can take both points to be on the same sublattice, then if we expand the cosines in terms of exponentials, we'll get contribution with a difference in heights. And we'd also get terms with a sum of heights, but you can see that you can increase H by a constant at no cost in energy. So when you integrate over those displacements of H, the terms which don't have a height difference in the exponential will average to 0. So this is the term that we need.
What are exactly the sublattices?
Well, on the triangular lattice, I can introduce 3 sublattices, which I'll call A, B, and C, in such a way that the neighbours of sites on one sublattice belong to the other sublattices. So, for instance, sorry, that blue is probably not very legible, but and then, for example, this site would be A, and this would be A, and so on. And this sublattice structure appears in the details of the correlation function, but it appears as something that gives you an oscillating amplitude when you go from one sublattice to another. So it's not something that we're as interested in keeping track of as any power laws which have more of the long-distance physics in them.
Yes, I have actually two questions. When you say h plus 6 equals to h, you mean that you don't care about the actual value of h, but you care about the value between 0 and 5. Is that it? I mean, the value of 7 or 1.
Yes, yes, yeah.
And my second question is about this phi of r. Phi of r should be also a closed-grain function, isn't it? So I'm not sure. I don't understand then why it can vary on one sublattice.
Well, it's just that phi should take one of these three values according to which sublattice I'm focusing on. So maybe I shouldn't call it phi of r if r is some coarse-grained variable. I should just call it phi with a sublattice label. Yeah. Okay, so now things are reasonably simple. We have a theory which was like this, and the significant thing is that since it's only quadratic in H, it's just Gaussian, and so we can work out these averages exactly in a reasonably straightforward way. And when we do that, well, we can say straight away that this will be the exponential of, and if we average this over a Gaussian distribution, we get minus and then we have to work out the mean square height difference between 2 points using this theory. And I'm in two minds as to whether to go through the details on the board or leave it as an exercise for you.
Are there higher order corrections to that you wrote down, or is that?
Well, the corrections are something that I also want to discuss. Okay, would you be happy to have this Gaussian integral left as an exercise, or would you like to see it? I guess some people already know this terribly well and others not. What's the preference?
Well, I would be interested to see it. But if I'm the only one, then I agree with anyone.
Okay. Okay, so basically we want to diagonalize this by Fourier transform. If we introduce an H of Q, if I take an L by L system, so that I have an applied periodic boundary condition, so I have discrete Qs, then I can write H of Q as the Fourier transform of the height field. And then H of R will be the inverse transform. And if I Fourier transform this effective Hamiltonian, then because of the gradient, I get q squared and now if I think about the average that I want to compute, I should substitute for the h's in terms of this Fourier transform, and what I get is well, the first point is that the different Fourier components of H are uncorrelated with each other, so it's only the diagonal terms that contribute, and what I end up with is okay, so this factor comes from the difference in coordinates, and this obviously comes from averaging the different Fourier components. And then when the system size is large, I can turn this sum over Q into an integral, and so what I get then is the 1 over L squared with the sum gives me a 1 over 2 pi squared and an integral over Q, and I have this 1 minus cos Q dot R, and then if I work out the average of H squared with this Hamiltonian, I get 1 over K times Q squared. And so the angular integral I can do and get a factor of 2 pi. So I have 1 over pi k, and then the radial integral, I have q dq, and that cancels 1 power of q, so I have dq over q. And the factor of 1 minus cos q dot r means that I have an effective cutoff when q is very small, which is of order 1 over r. And then I have a maximum q, which is 1 over some short distance cutoff, which is the remnant of the lattice scale. So this integral gives me a logarithm, and so what I have is 1 over pi k times the log of the distance. So, any questions on the details of that? So, if I put everything together, then I have a logarithm in the exponential. So what this is r over a to the minus some constant, which is pi over 18k, and the 18 obviously reflects this periodicity of the height field. Okay, so something quite useful and important comes out from doing that. I mean, firstly, we recover power law correlations, but more significantly, the effective theory that we wrote down for H had one dimensionless parameter in it, which is this K, which you could call a stiffness to fluctuations of the height field. And up to this point, we had no way of knowing what value that parameter took. But at this stage, we see that its value is actually quite important because it determines the power in these correlation functions. But fortunately, we do in fact have an exact value for this power because from the solution to the Ising model on the triangular lattice, we know that this power should be 1/2. So what this tells us is that we can identify K as being pi over 9.
I'm confused because that's when the Ising model is at criticality. Why do we use this?
No. Yes, okay, it's a coincidence that happens to be also for an Ising model at criticality, but this is really different physics, I think, unless there's some hidden connection. So if you had the triangular lattice Ising model with ferromagnetic interactions, then it would have a finite temperature phase transition, and at that critical point, then, as you're saying, you have power law correlations. But that's, at least on the face of it, quite different from what we're discussing here, where we have antiferromagnetic interactions and no phase transition at any temperature, except in a certain sense the zero temperature limit is like a critical point in having these power law correlations.
You calculated the correlation for the same sublattice if you do it for different.
Well, for different sublattices, you just have combinations of these phases, which would give you negative coefficients between spins on opposite sublattices.
As you increase the temperature, don't expect to get through the phase where you have like
Sure.
gas, but you do like
Yeah, sure. No, that.
transition from power law to exponential.
Well, in fact, it happens as soon as you go from to non-zero temperature, and that's one of the other things that I want to mention. Okay.
Is this value above or below the critical value for BTT transition?
Vortices are unbound. So, yeah. These are all points which I wanted to make. Whether I can fit them into 5 minutes, we'll see. Okay, so there are a number of things to discuss. So the point is that when we started this mapping to height fields, we had something that was completely precise, but at that level, the height field had to take integer values. So we can imagine that if we hadn't simply coarse-grained and written down this grad h squared as our effective Hamiltonian, we would have had other terms, and one of the other terms would be something that pins the height field to integer values. So you might write down something like that with, I guess, a negative coefficient to prefer the integer values. So the next step would be to check with RG whether a term like this is relevant or irrelevant, at least when this coefficient is small. And you can do that with standard momentum shell RG. And what you do, what you get from that is that this is irrelevant if the stiffness that appears here is small enough. So it's kind of plausible intuitively, because if this stiffness is small, then the fluctuations of the height field are large, and this term gets averaged out. And it turns out to be irrelevant if k is less than pi over 2, and the value that we actually have is smaller than that, and so this is it's okay to leave this term out and just to focus on that. And of course, we can think of other perturbations that you might add, but this turns out to be the leading contender for something that could be relevant. Okay, the one other thing that I have to talk about is excitations out of the ground state, and maybe I can squeeze that in. So if we have 3 upspins on a triangle and we apply this rule of increasing H by 2 when we go across a frustrated bond, then we have H plus 2, H plus 4, and we come back to H plus 6. And because we're no longer in the ground state, we no longer have a single-valued height field. So this is a sort of vortex in the height field. But it costs an energy compared to a ground state triangle of 4J. So these vortices are absent in the low temperature limit, but as soon as we go to non-zero temperature, they'll be present with some density that's roughly e to the minus 4 beta j. And in general, in these kinds of height models, vortices might either be bound together with antivortices in pairs if you're below the BKT transition, or if you're above, they'll be unbound. And with this value of the stiffness, it turns out they're unbound. So as soon as we go to non-zero temperature, we get a finite correlation length, and these power law correlations only extend as far as that correlation length. But the point is the correlation length can be very long at low temperatures, and it diverges in the low temperature limit. Any final questions? I'm sure I should stop now.
Is the growth of the correction length typical of KT, exponential of 1 over square root of temperature, basically? So can I view this system as having BKT transition at T equals 0? Or,
No, it's different from that. So the point is that the value of the stiffness is well above the critical value for the BKT transition. And so what controls the density of vortices is simply their fugacity, which involves this excitation energy. So what happens is that the vortex fugacity goes to 0 as you go to 0 temperature, but in an elementary way determined by the energy cost rather than by anything to do with correlations.
Just a question on the Gauss-Grain approximation. As H goes from one thing to another, it goes from a finding value, gets a finding value. How do you do the procedure?
Yeah, okay. So because of that, I think it's nice to introduce this intermediate step, which I mentioned, which is that we can, instead of discussing heights defined at sites, we can talk about heights that are defined at the centers of triangles. So that introduces some averaging, and it turns out that some states, these states with flippable spins, are flat in that language.
So you have to take some big regions, so that's H plus
Well, all right, so that means that already microscopically you've got configurations which are flat, and then it maybe seems more reasonable to average. But, yeah. Okay, right, let's finish. Thank you. So the point is that you have to be a bit careful in terms. So this really is an energy in the original, but everything to do with systems. You might like to call it energy, but in the original Latin model it was now, because we have this we'll have the usual to their energy and all the phenomenology DKT transition.
Yes.
They're running down the hill. Hey, I missed one thing.
Right, so the point is that first of all I can calculate spin-spin correlator it falls off with the power law and then secondly I can look up calculate safety find the power up. And so that's how you work. Well, I mean, I need to look up the treatment of triangular lattice
No.
I just need to ask again because I completely missed the point. Why was the mean field breakdown? Like where exactly is the
Right. Well, I mean, the difficulty that you have is that you don't know what to do below the temperature that mean field theory would normally tell you is the ordering temperature. So the point is that if you take some unfrustrated system, then you find a mode at some wave vector becomes unstable, and so in the square lattice antiferromagnet that I mentioned briefly, you get ordering at pi, and so then you know what to do. You know that there's order parameter develops there, and the magnitude you get by balancing the quadratic term against the quarter term in the usual way. But here, you've got a whole set of states in reciprocal space which become unstable at the same temperature.
Okay.
And so you could do what you normally do in mean field theory, picking out one particular ordering pattern, but it would be completely arbitrary.
Where did we see where did we see in the mean field theory that we have several solutions for the lowest?
Oh, well, that's the consequence of having this flat band for the eigenvalues of the exchange matrix. because the ordering pattern is normally into one of the states that minimizes the exchange matrix eigenvalues, and normally there's just some finite set, and now we have our infinite set.
Okay. Thanks.
So when we derive the effective Hamiltonian, we put this k as some logical constant, and we were just happy to have it appears in the correlation function. We have the exact result. If we would be more careful, could we determine from the exact model, or when we build up the Hamiltonian?
No, I think that would be essentially hopeless.
Okay.
I mean, these coarse graining approaches have some good sides and some bad sides. And the good side is that it gives you a clean way of getting at the long distance physics.
Mm-hmm.
But the bad side is that it has this dimensionless parameter, and you'd better find some different way to determine it.
So what if you don't have an exact solution? You do numerics or experiment?
Yeah, numerics. Yeah.
Okay, thanks.
So I think my question was related to this. So once you have fixed the effective Hamiltonian or K parameter, what is the advantage of using this coarse-grained Hamiltonian as opposed to the exact solution? Are there correlation functions that you can compute very easily with this, but not with the exact solution? So I'm sort of looking for motivation to mention this already.
You can use it. Well, there are probably several points to make. So, one is that I'm introducing this now to illustrate some ideas which are going to be useful in other situations where we certainly don't have an exact solution. But even in this case, there are lots of things that it would help you do that you couldn't do with the exact solution, and it would help you think about the effects of perturbations that you could add to the model that wouldn't be that you couldn't handle exactly. I mean, so for instance, something that's been in my own research recently has been studying a system of stacked triangular magnets, and so that was an access
This is when you have a coupling of these Gaussian theories.
Yeah.
The coupling is probably some central type
Yeah.
term. I see. Okay. Thank you.
Sorry.
Yeah.
So you mentioned that if the two bands overlap at some point, you get this parallel correlation.
Well, there's this.
Or is it something that you can't do it in?
Okay, so at that stage we were talking about correlations as being given by the projector onto the flat band. So this projector we could think about either in reciprocal space or in real space. So in real space the claim is that it has, or not in this triangular latticizing model in fact, but in some of these other systems it has a power law for it. So to get a power law in real space, you need some kind of singularity in reciprocal space. The link between the power and the singularity is quite definite. And so that means that we want to look for how there could be singularities in this projector in reciprocal space. So in reciprocal space, we've got these three bands that these several bands which are to do with the different sites in the unit cell. At some arbitrary wave vector, it's almost guaranteed that projection onto a particular band will be smooth as a function of wave vector. But the one place where you can have singularities is where bands touch, and then you have the kind of singularities that people are talking about in relation to Dirac points and so on.
Science question.
Yeah.
So it's about funding for next year, whether it's confirmed and we get another year's project.
Yeah, sure.
Okay.
You haven't had notification?
Well, not an official one, I think. It's just that I'm moving into a flat and they want to have like a proof that I'm going to have enough income. And I'm about to write to that I'd like such a document or something, but
sure, no,
whether I can refer to the fact that you told me that I'm going
no, absolutely we can. And if you like, copy the message to me, or I've signed the relevant forms.
Okay, then
asked Michelle to do that. A long time back.
Okay, all right, thank you.
Tiens, tout de suite vérifier que cette fois-ci le micro
oui. Oui, parce que non, tout est bon. Le problème hier, c'était...
Tu crois qu'on avait fait une...
Non, c'était avant. Et nous, on n'a pas vérifié parce que c'est vrai que d'habitude, tu vas sur les microns.
Oui.
Tu mets on-off en haut.
Ah, d'accord, oui.
Alors que là, en fait, c'est là, sauf que du coup, en fait, c'est resté sur...
D'accord. Donc on me voit faire le pitre, mais on n'entend rien.
Bon, je te laisse te brancher. Tu te branches. Donc ça c'est bien. Donc j'ai pas compris, est-ce que c'est branché? Non, c'est...
Tout est bon, tout est bon.
Tout est bon? D'accord. Ah oui, tout est bon, d'accord. Oh.